Today we study the X24, the first law of thermodynamics. It is a conservation of energy, including heat energy. Find the full statement regarding the work dW equals PdV. P is pressure. dV is a change in volume. This is the original volume, pressure. A gas is in a container of the shape of a cylindrical container whose cross-sectional area is A. The shape has changed, keeping the cross-sectional area the same, and we have a displacement of a piston by dx. Then the force applied by the gas inside the container has a pressure, and if we multiply the cross-sectional area, it becomes a force. The force multiplied by the displacement is the differential work. If I substitute this one into here, pressure, cross-sectional area, and displacement. And this AdX is actually the change in volume. Hence, the work done by a gas, dW, is eventually expressed as the pressure multiplied the change in volume. This one is defined only if the pressure P is well defined. That means the gas is in equilibrium at some temperature with the external pressure outside the cylinder of the volume. So the pressure inside and the pressure outside should be the same. And they make an equilibrium. Hence, the pressure inside the volume is well defined, and force is well defined, and the work is well defined. The formula is applicable independently of the shape of a container. It doesn't matter whether it is a cylindrical container or a sphere, anything else, that's fine. The dW is a positive if the volume of the gas increases. That means this one is a positive. The gas applies force to the external it is always toward outside. The gas wants to expand. The pressure, origin of the pressure is the motion of molecules. It collides the wall, and there is a wall, molecule collides, and it bounces back. In that case, the momentum, initial momentum, is transferred to the wall. So the pressure is always to the outside. If dW is negative, because the pressure is a positive definite, so dV must decrease. The force PA is the cross, here A is the cross-sectional area of the cylinder, that's fine. We have pressure P and have an infinitesimal expansion by dV, okay? And dV depends on, expression for dV, it depends on the shape of the container. Spherical container, we have a sphere. Radius changes to R2 dr. The pressure is normal to the surface, and they must be the same everywhere. Then pressure multiplied by volume change, and volume change should be 4 pi r squared, that is area, multiply the differential radius. So 4 pi r squared dr multiplied by pressure. So this is a question asking you to express dV in terms of the specific variable. So cylindrical container of a height h expands from r to r dr. Here height is kept and radius changes. Then the volume change should be a kind of, we have dr, this is dr, and area is h multiplied by 2 pi r. So thickness, the width, height, so 2 pi r dr multiplied by h should be the change in volume. Height changes, radius is constant. In that case, height changes dh and radius is constant. So what is the area? Pi r squared. So pi r squared dh pressure. If this one is negative, shrinks, right? dH should be negative. So R is positive, P is positive. Regarding a free expansion is expansion of gas. I use different color to identify the different molecules. For example, air is not a pure substance made of a single type molecule. Instead, we have oxygen, nitrogen, and so on. We have a partition, and the other side of the container is in vacuum. Vacuum is nothing, because there is nothing. Without any other external force, this beam should move, because a vacuum cannot apply any force and any pressure to anywhere. However, this side we have a certain pressure, and this gas gives a force to this part. So this partition should be kept held by something else. So external force should be applied to keep it. Suddenly, if you remove this partition, the molecules, because the molecules are always moving very rapidly, unless you have 0K. So they are moving very quickly, and suddenly, in a short time, the vacuated part will be filled by molecules. And after it takes some time to reach a thermal equilibrium at temperature T, and it has a certain volume and a certain pressure. Okay, that's called free expansion. Law of action and reaction states that the force applied by the gas is toward this direction to the environment is a zero. Okay. You have a massive object, your hand. You are sustaining a massive object. This object gives a weight. To have an equilibrium, you must apply the same amount of force, but in opposite direction. This is a unit vector along gravitational acceleration, and this is a unit vector in opposite direction. What happens if I remove this away? Then my palm does not apply any force. My palm does not apply any force. So when this gas makes a free expansion to this state, during this expansion, the gas does not work at all. Even though it has its own pressure, in order for this gas to work in either positive or negative sense, there should be something to apply the force to make a complete cancellation in equilibrium. But there is nothing is applied, so this gas does not apply any force. So F equals 0, so F times the dx should be 0 too, and integral of F dx should also be 0, because F is always a 0. That's the reason why the gas does not work during a free expansion. The environment does not exert any force on the gas during the free expansion. That's right. It is action and reaction. If action is 0, reaction must be 0. The pressure of the gas is not defined well during free expansion. It's not defined during the expansion because as soon as this partition is away, the volume is not defined well. I don't know the boundary of this gas until it reaches an equilibrium. Only if there is a thermal equilibrium, we can define pressure, volume, and so on. However, temperature is during the expansion, temperature is well defined. The reason is that the temperature is determined by the average kinetic energy of molecules. average kinetic energy. There is no mixture at all from the beginning until the end. These molecules do not change their own kinetic energy at all. So average kinetic energy should be the same during the whole expansion process, except for the temperature. Nobody knows the pressure and volume between the two, between the initial and final state. They are in equilibrium. But during this process, no equilibrium. So nobody knows how to compute the pressure, how to compute the volume of the gas. The work done by the gas under free expansion is zero. Yes, correct. Law of action and reaction states that the force applied by the gas to the environment, we have isobaric expansion. Isobaric expansion. Have you heard about the barometer? Barometer measures the pressure. Iso means the same. Baric. Same pressure. Isobaric pressure is a constant. This is nothing but the constant pressure process. Isobaric is a constant pressure process. So constant pressure. Okay, so pressure multiplied by the cross-sectional area is the force. Environment exerts force to the gas during the isobaric expansion, right? So we have a constant pressure to the outside, and environment applies the same pressure opposite direction. The work done by the gas always expressed in terms of PDV, and if the cross-sectional area, this is a cylindrical container pressure, dV is A times dx. Work done by the environment, because it is an energy conservation. If the gas does work by this amount, but in that case, the same amount of work is done by, in the negative sense, by the environment. To make, if you add these two, there is nothing. It means energy is conserved. If gas loses some amount of energy, then environment accepts the same amount of energy. If the gas loses a certain amount of energy, then the environment accepts the same amount of energy. That is the conservation of energy, and that is nothing but the first law of thermodynamics. The sum of the work done by the gas and the work done by the environment is zero. Yes, it's a conservation of energy. Still, we are working on cylindrical container of the cross-sectional area A. While the temperature is fixed, the pressure, isothermal, same. Thermal, temperature, same temperature process. Same temperature. Isothermal, same temperature process. While the temperature is fixed, the pressure is not fixed to P. And actually, you will find that PV is proportional to temperature. And if the temperature is fixed, product of pressure and volume is constant. So actually it is pressure is anti-proportional to the volume. The heat reservoir supplies a positive amount of heat. Let's see. Expansion. 여기 we have reservoir and gas expands. Delta V is a positive. Gas expands. But the temperature is the same. Temperature is equivalent to up to over factor KB. Temperature is the energy. So it is proportional to temperature is the internal energy. Temperature is internal energy of gas. This gas does work, so dW is a positive. The first law of thermodynamics says dQ is accepted by the gas. It does work, and accepted loses remainder. Change in the internal energy. This is the first law of thermodynamics. We have a constant temperature. That means energy is conserved. So energy is conserved. There is no change. Haha. Heat reservoir gives heat, dQ, and the amount of work done by the gas, dW, they must be the same. Isothermal. Internal energy is invariant. According to the conservation of energy, that is the first law of thermodynamics, if you have internal energy constant, then supplied heat by heat reservoir to the gas is exactly the same as the work done by the gas. If I want to compute the work done by the gas at an isothermal process, we have pressure is anti-proportional to the volume. So this one is replaced with 1 over V up to over constant. Then this is the nothing but the differential of log. And in physics, in mathematics, so you can write it, but in physics, log that is composed of many terms of different dimensions. It is safe to express this function in terms of scaleless variable, that is V over V0, that one does not carry any physical dimensions. Sixth statement regarding the work done by a conservative force. Work depends only on the position, initial and final, right? Work is independent of path, Any path, only initial and final position does matter. Work is independent of the time interval. As long as initial and final are known, it doesn't matter whether it takes a certain path or not. How long does it take? That doesn't matter at all. The first conservative force is irrotational, right? We have a cyclic process, and we have volume, pressure, plot. Remember, the work done by gas is a PDV. Haha, PDV means a pressure curve. Under the pressure curve, this is the area, and that area represents the work done by the gas. This is the work done by the gas from A to B. This is the work done by the gas from A to B. And what about this? This is the work done by the gas from B to A. Aha, we find the path dependent. This work is greater than this work. And this work and this work, they are the same in magnitude, but in opposite direction. This work from A to B is a positive, but B to A is negative with the same amount. As a result, this integral, this is positive by this amount, this is negative by this amount. If you subtract, then you end up with the area of this over area. This is the work done by a gas that is making a cyclic process. Cyclic means it returns to the same point, just like engine or refrigerator. If it is making a cyclic process, it returns to the same point repeatedly. So during a single cycle, the work done by the gas is the area inside this over curve. Energy consists of total kinetic energy and total potential energy. Gas is just a single phase. So single phase, we don't have to worry about this. But if a matter changes its shape from ice, water, and vapor, when they make transformation, phase transition, during this period, potential energy does matter. That's quite important. However, during a single phase, only the kinetic energy concerned. The heat of transformation is relevant to the phase transition, and that is corresponding to the potential energy. Process involving a single phase is independent of potential energy. Right, correct. If dV equals 0, then the gas does not work. That's fine. The process invariant volume, dV equals 0, the gas does not work at all. If the gas does not work, supply the energy is directly transferred to the internal energy. Internal energy is always proportional to the temperature, and that results in the temperature change. Overall coefficient is called the heat capacity of the constant volume process. If you allow the change in volume, the heat capacity, for example, the constant pressure process, the gas can expand. So it requires another amount of energy to expand. Therefore, the constant volume process, the heat capacity is smaller than the heat capacity of constant pressure process. From this identity, we can take the ratio, internal energy change. If I divide this internal energy change by the change in temperature, we can obtain the heat capacity of constant volume process. Number 9, internal energy of a gas of constant volume. Constant volume, dV equals 0, so PdV dW equals 0. Therefore, dQ must be the internal energy. Okay? The gas does not work. Gas does not work. Okay? Supplied heat is solely transformed into internal energy. Heat is completely transferred to the internal energy. Correct. The temperature change is linearly proportional to the supplied heat because it is a constant volume. It is always expressed as CVdT. Linearly proportional to energy is linearly proportional to, right? The temperature change is greater for a sample of a smaller heat capacity. So temperature change, because the CV is over coefficient, smaller heat capacity. If this amount is the same, if this is bigger, then this one is smaller. This one is a CV is smaller, the DT must be greater, right? Later, we will learn the equation for gas. This is ideal gas equation. Number of molecules, Boltzmann constant, absolute temperature, pressure, volume. Temperature T is uniquely defined at a single point. Temperature T, PV over NKBT, KB from this. This one is true only if N is large and we have a thermal equilibrium at temperature T. If there is no thermal equilibrium, then we cannot make use of this ideal gas equation. Given temperature T, the pressure, divide both sides by V, then we obtain this one. If T is constant, then the work done by the gas, this is constant, number of molecules constant, this is constant. So PdV is the work done by the gas, and P is this, and we have a constant, NKBT, all constants. We have this integral, and that is log. So this is a final volume, initial volume. So the final answer is log 2. The change in the thermal energy of the gas can be computed as internal energy, dQ. If V equals dV equals 0, CV dt. That is internal energy. And always internal energy can change it of internal energy can always be expressed in terms of CV dt. And if you integrate by a finite amount, you end up with delta and delta t. 11. A gas of constant volume constant volume, PDV, dW equals 0. The heat capacity, accept the heat, yes, right, constant volume, D internal, and CV dt, memorize. The first law of thermodynamics is useful to describe this process because PDV equals 0, so we have an identity. The change in the internal energy, change in internal energy is identical to dq, and that is identical to CV dt, right? According to the first law of thermodynamics, this is the first law of thermodynamics because gas expands, constant volume accepted, okay. If if the gas expands, dV equals is a positive. Heat transfer to the gas. Heat transfer to the gas. The full expression is this, and this is the internal energy, and that is expressed in terms of CV. Okay, if dV is positive, then this is positive. Therefore, this one is greater. dQ is greater than CV dt. Okay, so this one indicates that in general, C is greater than CV. This is dV is a positive. This is V equals constant. The first law of thermodynamics is a consequence of energy conservation. This is energy conservation. Input, output, and remainder. 12. Free expansion. Free expansion. Internal energy of the gas is preserved. In free expansion, dQ, PDV plus the D internal. Although we have positive, however, the pressure should be used only if the gas is in equilibrium with outside. So outside vacuum, gas, although it has its own pressure, there is no way to use this force to push the partition because it is a vacuum. This work is always a 0. And internal energy, this free expansion assumes there is no heat transfer too. So input equals 0, free. So this one is 0, this one is 0. We end up with the fact the internal energy change equals 0. Whatever amount of integral, finite, and this should also be 0 because it is always a 0. Pressure decreases. Okay, if you consider PV equals NKBT and temperature is a constant, that means the PV is constant. Pressure times volume is constant. Even though we do not know the pressure and volume in the middle of free expansion, at least we know the initial and final value for the pressure and volume when they are in equilibrium. Therefore, PV equals PV, initial, final. So we divide both sides by final, then final pressure is P initial, V initial divided by V final. The gas does not work during a free expansion. That's correct. There is no heat transfer during a free expansion. Find the full statement regarding an isobaric constant pressure. Isobaric process of gas with the heat capacity CV at constant volume. The gas accepts the heat delta Q. Pressure P is constant. By definition, isobaric process is a constant pressure process. So pressure is constant. That's correct. The work done by the gas is PdV integral. However, this pressure is constant. So this integrand is constant. So I can factor this P out, and this one becomes a trivial integral. It is always a delta V. Because V changes from V to V, delta V equals 2V minus V, that is a V, so this is PV. That's correct. The internal energy changes, energy conservation should be used according to the first law of thermodynamics. Delta Q equals P delta V plus delta E internal. P delta V, according to this is PV. Just change by delta V. Then internal energy change should be delta Q subtracted by P delta V. That's correct. The change in temperature. Internal energy is this, and internal energy change is always expressed as a CV delta T. So change in temperature can be obtained by dividing this one by CV. That's correct. Delta Q is greater than CV delta T. Delta Q, right. From this expression, delta Q equals CV delta T plus P delta V. And if delta V equals positive, this is positive, so it is always greater than CV delta T. Okay. Number 14, find the false statement for an isothermal, same temperature. Same temperature process from the initial volume VI to the final volume VF. Because delta T equals 0, internal energy is conserved, right? The internal energy, delta internal energy is always expressed in the CV delta T. Delta T equals 0, this is 0, therefore internal energy is conserved. Because the internal energy is preserved, energy transferred to the system is the same as the energy released by the system. The first law of thermodynamics is input, output, and the remainder. And the remainder vanishes because the temperature is constant. Therefore, this input should be the same as output. This is energy transferred to the system, delta Q, and the energy released by the system is a PDV. Okay, the work done by the gas is the same as the heat supplied to the gas. They are the same statements. If PV equals NkBT, ideal gas equation, then the work done by the gas, because it's isothermal, this is constant, so pressure should be NkBT over V, and temperature is constant, so it is factored out. NkBT is factored out. We have integral. This is the log and final initial log final initial volume ratio. 15. Find the force statement for constant volume process for the gas of heat capacity CV at constant volume. The gas accepts the heat delta Q and the change in temperature is delta T. Okay, the work done by the gas, PDV integral, constant volume. Integral doesn't exist. This V doesn't change, so it is 0. The heat supplied by the gas is the same as the internal energy, because energy conservation, P delta V delta internal energy, and PDV vanishes, energy supplied to the gas. The internal energy change, they are the same. The gas does not spend energy through work because there is no work. The temperature is increased. Temperature is always expressed in terms of CV, delta T. So delta T is delta internal energy divided by CV, right? The sign of delta T is the same as that of delta Q because the CV is a positive definite. Sign, if it is a positive, it is positive. It is negative, it is negative. 16. Find the false statement for an adiabatic. For a gas of heat capacity CV at constant volume. Adiabatic, there's no heat transfer. No heat transfer is called adiabatic. Delta Q equals 0. Adiabatic process does not have any heat transfer. Delta Q is 0. Because delta Q equals 0, First Law of Thermodynamics says P delta V plus delta internal energy. Aha! If it works, if the gas works, then the internal energy decreases. If it is a positive, if it expands, the energy is lost, so temperature decreases. If it shrinks, if delta V is a negative, then internal energy increases because there is no heat transfer from and to the heat reservoir. Because there is no heat transfer, the work done by the gas is identical to the loss of internal energy. Yes, correct. And this one is expressed in terms of CV delta T. That's the reason why we have negative sign. Sum of this is 0. Okay. The temperature decreases if the gas expands. The temperature increases if the gas shrinks. That's correct. This process is well understood under the first law of thermodynamics, all right? 17. Find the false statement regarding the difference after a single cycle in a cyclic process. After a cycle, it returns to the same temperature, same pressure, same volume, everything, same macroscopic physical variables such as temperature, pressure, and volume. Cycle returns the same physical variable. That's quite important. Hence, the internal energy is invariant. Sure, because the temperature is the same, the internal energy doesn't change at all. Since the internal energy is invariant, the amount of work done by the gas is identical to the heat transfer to the system. Delta Q, input, delta W, that is a P delta V, delta internal. During a cycle, returns to the same state, temperature the same, so internal energy is the same. This one vanishes, therefore supplied heat is completely transferred to the work. So conversion of heat to work by 100%. After a cycle, it returns to the same pressure, sure, same pressure, and same volume. 18. We consider the conduction of heat between a heat reservoir of constant temperature, TH, this is hot, a cold reservoir of temperature, TC, it's cold, connected by R, A. A uniform material of cross-sectional area A and length L. Cross-sectional area A and length L. We have temperature TH, hot and cold. The heat is transferred from the hot heat reservoir to cold heat reservoir. It takes a shorter time interval to transfer the same amount of heat if we increase the temperature difference. That's correct. It takes a shorter time interval to transfer the same amount of heat if we decrease L. Yes, it takes longer time if you elongate the length. It takes a shorter time interval to transfer the same amount of heat if we increase A. Yes, right. That's the reason why we increase the cross-sectional area of a radiator. The heat conduction rate, the amount of heat transferred by unit time, can be expressed like this. And actually, this expression is very similar to the calculation of electric resistance. Here, K, it depends only on the material rather than the geometry. And geometry appears in the cross-sectional area and length. And the R, if R is larger, the amount of heat transferred per unit time decreases. So that's the reason why we say R is thermal resistance. It is very similar to the electric resistance.